Hello, good afternoon. This is Amelie Ramirez. I'm the director of the Éxito program, the Latino Cancer Research Leadership Training Program. I want to welcome you all to our webinar this afternoon. Thank you for joining us. We have folks that are just, continuously signing on. So thank you very much. I'd like to welcome all the doctoral students, both from the Éxito students and the MTCPR program. We really want to thank you. We've got also Dr. Rena Pasek, who will be introducing our speaker in just a moment. But I wanted to go over just a few logistics with all of you. As you well know, today's webinar is one in a series that we hope to offer useful information that will focus on statistics. We've been trying to identify topics that are of interest both to our alumni, those individuals who are just finishing their master's and going into a doctoral program, and those of you who are currently enrolled in a doctoral program. And for some of us, statistics has always been something hard, and you all have identified this topic, so we're really excited that we can focus on that this afternoon, and hoping that fear will go away. But before we begin, there are a few housekeeping items that we'd like to keep in mind. If everyone will be muted during the actual webinar presentation, but you can write a question in the box at the top of the, in the box that's available to you on your webinar at any time. The organizer at the end of the session will announce the questions, and then Dr. Sugar will provide answers to the questions you've written. At the end of the webinar, you will receive a survey by email, and please complete the survey. We really need your feedback. We want to make these webinars instrumental and helpful to you. So we really would like to know what you thought about them, how we could improve on them, and if you have any other suggestions, we are open to identifying topics and willing and able to identify other speakers that might be of interest to you. So with that, I'd like to invite Dr. Rena Pasek from UCSF to introduce our speaker this afternoon. Rena?
Thank you, Amelie. Hello, everyone, all the Éxito and MTP-CCR alumni. I am really thrilled to be able to bring you today's webinar. First, I have just a couple of quick announcements. First, I want to thank everyone who provided feedback to my webinar on grant writing. It was very helpful. We are going to take your suggestions. We're going to have a series of 2 or 3 grant writing webinars in early in 2018. So watch for announcements on that. And also the first webinar that I did last month, or month before, I'm not sure, is available on the archive and on the Éxito website on the archive, and anyone can access that. And that'll be true for this webinar and all our webinars, while the live webinar is only open to our Éxito and MTP alumni. Anyone can access, and we welcome people making use of the archives. And the last announcement I have is that MTP folks, you will see an email today from Vanessa Mercado announcing our recruitment for 2018. Please share that information far and wide and help us recruit another fabulous class. Okay, now it is my great pleasure to introduce Dr. Catherine Sugar. We first got to know Dr. Sugar when Dr. Marjorie Kagawa-Singer at UCLA brought her to speak at one of our doctoral student retreats, and she was fantastic. The group really appreciated, enjoyed, made great use of her presentation. So I was very excited when she was willing and available, even eager, to do this webinar for us. So Dr. Sugar is a professor in the UCLA Department of Biostatistics, Statistics and Psychiatry and Behavioral Sciences, and a fellow of the American Statistical Association. She received her PhD in statistics from Stanford University. And she has worked in quite a wide range of topical areas: HIV, dentistry, oncology, cardiology, infection control, and she has methodologic expertise in things I have no idea what they even are. But what's most important today is that she knows how to talk about statistics to people who are just starting out to learn this important and challenging discipline. And she has a great way of talking about it and thinking about it that really demystifies. So enough of me. Welcome to Dr. Catherine Sugar.
Hi, everybody. Let's see. Can everybody see me now and hear me clearly?
Yes.
Wonderful.
Yes, we can.
All right, great. So thanks for the kind invitation. I've very much enjoyed my previous interactions with this group, and it's great to get to do it as a webinar. As was mentioned, I'm on the faculty at UCLA, and one of my big roles, both as a faculty member and director of the Statistical Consulting Corps for the UCLA Semel Institute, is to work with graduate students, fellows, and junior faculty who are maybe not so familiar with statistics and are trying to work it into their dissertations or their subsequent research projects. And I encounter a lot of statistics fear when I work with that group, so hopefully today's talk will give you some of my ideas about why you shouldn't be so afraid. The title of the talk, How I Learned to Stop Worrying and Love Statistics, comes from a 1964 Stanley Kubrick film starring Peter Sellers and George C. Scott, Dr. Strangelove, or How I Learned to Stop Worrying and Love the Bomb. And that's maybe relevant here for several reasons, but the one I want to emphasize today is that loving statistics really should not be strange, unlike loving the bomb, which I don't think any of us really want to do. Let's see, where is this? Here we go. So first of all, with regard to statistics fear, if you have it, you're not alone. Math anxiety in general and what I call statisticitis in particular are quite common. In fact, every time I start a new course, whether it's with undergraduates or our master's and doctoral students here at UCLA, I get a lot of this at the beginning of the quarter. Can I really do this? I'm not very good at math, et cetera, which is from my point of view frustrating, because I actually think that everybody can be a good basic user of math and statistics comments. So every statistics professor I know has some jokes and stories that they tell to try to diffuse this situation. I actually even had an exam once in which I was asking students to analyze some data about a disease, and the disease was statisticitis, and the factors that affected it were things like how far you were from the test and how many previous math courses you'd have, and so on. There's some other ones. This one was courtesy of my husband originally. He started it with his first MBA class right after our son was born. Michael is now 15 and he's a math geek, so probably he's not saying, please mom, no more statistics anymore. But this was one of the first diffusing slides that I or my husband ever showed. Comes up when I'm in social situations as well, and people say, what do you do for a living? Oh, I'm a statistics professor, and I get a lot of responses, none of which are terribly cheering, and to which I try to reply, well, yeah, maybe you didn't have the right professor, or maybe they didn't make it accessible enough, or well, maybe you should try a different kind of statistics class. So hopefully by the end of this, you won't be having any of those reactions, and I won't be having to try to explain at cocktails that I'm the person who helps you figure out whether having a glass of red wine every day is actually good for you. That example usually made people interested. So where does statistics fear come from? Well, there are a lot of problematical memes out there, and they start very early. One of the big ones is that the quantitative sciences generally, and math and statistics specifically, are hard, and that you have to be especially smart or you're not going to be good at them. I remember being particularly enraged one year when a new version of Barbie came out, which said, among other things, it was a talking Barbie, math is hard. It really made me want to write nasty letters to the company. Statistics does not have to be hard. It does not have to be abstract. In fact, it's one of the most practical of the quantitative sciences. And although there certainly is technical stuff underlying it, there's lots of non-technical stuff that's relevant to you. Some other problems that I think come up for people is that, as with any technical field, there's a lot of jargon and notation, and people find that intimidating. But in fact, everything about statistics can be translated into words. Another thing is the uncertainty. As we go through math in elementary school, middle school, high school, even college, we're taught that math is the class where there's a right answer. We can circle 5 or pi over 2 at the end of the problem, and that's it. But in statistics, you're actually dealing directly with uncertainty. I have an estimate, a best guess for what the answer is going to be, but I only have a certain amount of certainty about it. It might be off by a certain amount, and that makes people uncomfortable. Another issue is the logical framework that statistics uses. It's kind of backwards reasoning. You start by assuming the thing that you don't want to be true, and then try to show that that's wrong. And so people's basic intuition about statistics often doesn't feel right to them. And so learning to think in that logical framework can be tricky. And then finally, a lot of statistics courses, instead of teaching conceptual ideas and using examples that are easily accessible to the people in the class, focus on the calculations, and everything is done in terms of dice or coin flipping, which, while at least accessible to everybody, probably doesn't put it in the framework of the research problems that you would like to work on. So what's the reality that it is opposed to this? Well, first of all, as with any other field, there is a large range of abilities. There may be an initial learning curve to statistics that's harder than some other fields, but it isn't really overall harder than anything else. To be really, really good at it requires the same level of skill as to be really good at any other field. It's also not the case that you need to know advanced mathematics to be a successful user of statistics as a researcher. So if you want to develop new statistical methodology, yes, you need to be a mathematician, but to be able to analyze real data in your field, you don't. What you need to do is learn how to translate the statistical terms and notation into English, and how to interpret the output from computer packages as it relates to your subject. On the issue of uncertainty, it's true that that can be a little bit scary, but it's also where all of the interest lies. Problems where you just, at the end, circle pi over 2 and are done are not so exciting. The exciting stuff is, what does this mean I should probably do for my patients to, to talk about public policy with people in government, to translate findings to the community, and all of that inherently involves uncertainty. The good news is there's a systematic set of principles and techniques that you can learn that will give you confidence when using statistics, and I'm going to go over a few of those and then give you some examples which will hopefully show you that statistics isn't as remote as it may seem. So the first big piece of advice is to trust yourself. Statistics is actually something that you do every single day without realizing it. We're all assessing probabilities, we're all making estimates, we're all making comparisons and basing decisions on them. And as a result, especially with regard to your own research, your scientific intuition is going to stand you in good stead. You should never do statistics just as a mathematical calculation divorced from your scientific knowledge. You should use it to complement your knowledge. In fact, I often tell students statistics is just a way to formally quantify what you as an expert already know from collecting and looking at your data. So People have a lot of misconceptions about what statistics is. At this point, you probably don't have most of these, but all of them are out there. So recording stuff about sports teams. My son loves to do that, but it's not statistics in the sense we mean. It doesn't involve endless number crunching or data entry or mind-numbing calculations. Those are the things that would make it boring. It's also not really about figuring out ways to lie with numbers, though of course people can do that. It's not just abstract mathematics. I started life as an algebraic topologist. If you want abstract, go that way. Statistics, by comparison, isn't abstract at all, at least not if you think of it properly. And of course, it's certainly not something to be afraid of. There are a lot of things that statistics is. So statistics could have been used to save several of our space shuttles that didn't make it back. They can be used to understand elections, to identify genes or disease risk factors, compare different treatments, run the census, predict the stock market, and on and on and on and on. So almost every subject these days comes with data attached. And wherever there's data, you can do statistics problems. I once actually got a call from the Getty Museum in Los Angeles. They had a bunch of old furniture. It had metal handles and knobs and things. And they wanted to be able to tell whether those handles and knobs were original based on their metal content. That's a statistics problem. Now, I'm a biostatistician. That's not what I usually do. But in fact, I've been asked to work on problems as diverse as identifying the authenticity of ancient furniture using statistics. So if you want to use statistics, you can do almost anything. That's actually why I'm a statistician. I could never decide what I wanted to do, so I do everything. So what are some practical steps that you can take to make statistics a little bit less scary? So one thing you can do is to reinforce your mathematical background. And I'm not talking about things like real analysis or calculus. I'm talking about your basic quantitative skills. The next thing is to understand the basic conceptual framework that underlies statistics, which I'll go over briefly. Third piece that's really important is to learn the vocabulary. Statistics is a language. There are basic descriptive templates that you can always use to interpret results, and so you can use it to do translation. And then the final thing, and this is perhaps the most important one, is being willing to play around with your data, and in particular become proficient with statistical graphics. It turns out that if you have the right picture of your data, it will almost always tell you the right model and the right answer. If you can't see it in a picture, then it's probably not there. And most people, even if they're not very comfortable with complex mathematical formulas, are very comfortable with pictures. All right, so more specifically, some things that you can do. If you've taken, and at this point, for those who are doctoral students or certainly graduates, you probably have a number of statistics classes. One good thing that you can do, which I always encourage my students to do before their final exam, is to make a list of all the different statistical techniques and models that you've learned and create a flow chart to help you understand what techniques can be applied in what situations and what the underlying assumptions that go with them are. And then you can use that as a roadmap every time you have a new problem that you're trying to analyze. As I mentioned before, it's really important to let your intuition and scientific knowledge help you. So if you're taking a new statistics class, as you listen to the professor, you should pick out an example from your particular field, or if you've reached the research stage, the problem that you personally are working on, and try to translate the statistical terms they're giving you, the estimation problem, the hypothesis testing problem, the conclusions that are being drawn into a field where you know the variables and the likely outcomes really, really well. If you know what the answer should be for your particular problem, that lets you check against the models and tests that you're running. And finally, of course, you never have to do all of this alone. Most researchers in primary contextual areas don't do all their statistics themselves. They find a statistical collaborator to work with. That would be me. I work with lots of fellows at UCLA and many, many faculty members, and you'll be able to find statisticians to work with too. If you look around, you'll get the benefit of the support, and the statistician will be excited because they'll have a fun new data set to play with. And that's how most statistical research originates. I don't make up theoretical methods in a black box. They grow out of real research questions that I had to help somebody answer, and that suggested new approaches to doing things in the statistical world. So what math do you actually need? Well, the first thing to notice is that statistics is not just math. There are lots of people who are bad at math, but good at statistics. And really, you can use most statistical tools with just a good command of high school algebra and pre-calculus. This is actually a question that was one of the most memorable I had as a professor. I had a student come in and they were complaining about an exam I'd written where I'd asked them to write out what the problem was, solve it, and then explain the real world consequences along with explaining the graph that went with the problem. And they asked me, is this a math or an English class? I had taken off points because they'd given me a number with a circle around it and no explanation. And my response was, well, it's both. It's a math class, it's an English class, it's an art class, it's a class in ancient Greek with the notation, and a million other things. So don't think of statistics as just math. Think of it as the way you understand your data. Another thing that is really helpful, if you haven't already had it, is to read a book or take a course on the basics of formal logic. Statistical inference, which we'll talk about in a minute, is entirely based around a couple of core logical concepts. That's something that we often don't get in our undergraduate or graduate educations, and it's super, super helpful, not just for statistics, but also for being a competent consumer of information as a citizen. Specific mathematical techniques that are going to be useful. One thing is certainly understanding functions. So if you're about to go back and take another statistics course, it's going to be helpful to know what polynomials are. Those are functions like x, x squared, x cubed, the powers. It helps to remember what logarithms and exponentials are. Those get used in a number of statistical models. It's also important to understand what a model is. A model is very simple. It's just an equation that describes the relationship between a variable that you particularly care about, it's usually called your outcome variable, and other factors that you think might contribute to that outcome. So those ideas about functions and models are probably the key mathematical tools. It's true that if you want to really understand the methodology or develop new approaches because the data set you're working with has some particular quirks, then it's helpful to have some more advanced classes. And for those who are interested, calculus, both single and multivariate, and some applied linear algebra and matrix theory can be very useful. But if you're mostly going to be an applied consumer, that level certainly isn't necessary. So let me switch gears a little bit and talk about the conceptual framework that underlies statistics. There are actually two pieces to this, one of which I'll call probability and the other of which I'll call statistics. So thinking from the probability standpoint, there's some system, maybe it's the evolution of a disease epidemic, and you know what the underlying mechanism is, so how the disease gets, say, transferred from one person to another, and knowing what the underlying mechanism of the system is, you reason from it about what will happen next. So if I had a model of a disease epidemic and I fed in certain parameters like transition rates and how likely the disease is to kill somebody and so forth, I could then run that model forward and say, suppose a new infection was introduced, or maybe some new mosquitoes carrying Zika virus were introduced into an area. What would be likely to happen? How many people would get sick? How many people would die? That's a probability problem. You know the underlying mechanism, you reason forward to data, what will happen next. Statistics, which is the part that we're more concerned with here, is basically the reverse of that. You have a bunch of observed data, like when you think the mosquitoes came in, how many people got sick, how many people died, how rapidly the disease spread. And from that, you want to try to infer something about what the underlying mechanism of the system was. So in other words, you wanted to know what that mathematical disease model is. Statistics refers to going from a sample to the population or the model. So those two ideas are dual, and the reason that you get taught a whole lot of probability at the beginning of your basic statistics course, which probably seems the most abstract thing to start with and the least directly useful, is because the statistics process, the piece you're interested in, reasoning from your data to the population, depends on knowing the rules of probability. That's how you go back and forth between the two concepts. What do we use statistics for? Well, globally, statistics is about explaining variability in observed data or understanding uncertainty. And there are a lot of different sub-goals that go underneath that. One of those is estimation. You might want to estimate key population characteristics. Like, let me switch examples. Suppose that we were talking about smoking and lung cancer. You might want to estimate what fraction of the population smokes, what fraction of the population gets lung cancer, what are those fractions of people who get lung cancer among smokers and non-smokers, how many of them die from it, how long does that take. You can also use statistics to test theories about the population. So, for instance, you might believe that people who smoke are more likely to get and die of lung cancer. Can you show that that's true? Well, of course, when you do a simple test of that, it was found very, very, very early on that rates, both of acquisition and death from lung cancer, were much higher in people who smoked or people who didn't. But the tobacco companies tried to argue that maybe that was because people who smoked were also more likely to drink or to not have good exercise habits or to have different genetic backgrounds. And so it wasn't just about those two variables, but it was the entire pattern of characteristics that people had that might determine whether they got or died of lung cancer. And so more broadly, you can use statistics to try to find patterns in data. The area that I work in, which was described as being a little bit abstract, is really nothing more than trying to find patterns. I do what's called cluster analysis, classification, and functional data analysis. And all of those deal with trying to find patterns in large multivariate data sets. And we're all really good pattern recognizers ourselves. It's just not necessarily so easy to think about how you would write that down mathematically. But that's a major area in statistics. The kind of pattern that we usually in basic research problems are trying to identify is whether or not there's a relationship among two or more variables and what the nature of that relationship is. And there are a couple of pieces to that. So one is what the form of the relationship is. So you've probably mostly all learned linear regression. That assumes that the shape of the relationship between two continuous variables, when you plot it, is a straight line. But there might be curvilinear relationships. That can just mean differing returns. So if you give people more and more of a medication, cure rate might go up, but eventually it levels off. There's a limit to how much you need to give. Another question that people are super interested in is causality. I'm sure every statistics teacher you ever had jumped up and down and said that correlation was not causation. And that's true. You can have things that are related to each other because of some additional underlying cause, but we're generally very interested in causality. And so there are a lot of statistical methods being worked on now to say, well, how much can we say about causality and how can we tell if our data are consistent with a causal model? So that's certainly a key piece. And then the final big area that I should mention is making predictions. So when you build a statistical model, you can use it to say, yes, is there a significant relationship between some of the predictors I care about in my outcome? But you might also want to use the model, which is after all an equation, to generate predictions for future people. So that's a very important aspect too. And in most cases, when you're doing research, it's important to identify what is the question I'm trying to ask. Is it an estimation question? Am I testing a particular hypothesis or theory? Is there a particular kind of pattern I'm looking for? Is my question really one about a relationship? Am I trying to make predictions? That will help tell you the right technique to use. A couple of additional important terms. So I've already used the phrase statistical inference a couple of times. Inference here means nothing more than using the data that you have to draw conclusions about the population or system that you're interested in. In almost any research study that you do, you're not going to get to look at the whole population. It's going to be too expensive, too impractical. Some of the people may not even be alive yet or yet have the disease that you want to examine. So you're only going to get to look at a subset. And based on that subset, there are probably going to be quantities that you want to estimate or get confidence intervals for. There are hypothesis tests you want to run. And going along with that idea of hypothesis testing is the idea of the p-value, which basically just says how consistent your data are with the two competing hypotheses that you're examining. Okay. So the statistical inference is one big piece. In order to do statistical inference, you usually generate a statistical model. So a statistical model is an equation based on data, and that's where it differs from pure mathematics, that describes the relationship among multiple variables. The key phrase here is while accounting for uncertainty. So I'm sure that every one of you is familiar with a conversion formula, say from height in inches to height in feet, right? It's just a factor of 12 going back and forth. Or slightly more complicated, the conversion from a temperature in degrees centigrade to degrees Fahrenheit. So multiply by 9/5 and add 32. Those are both examples of what's called a linear model, right? So you can write your outcome y as a constant plus a second constant, the slope, times the variable that's determining it. So so in the examples I gave, both the outcome and the predictor were the same. We were just converting units. But of course, you might also be interested in, say, how somebody's weight depended on their height, their gender, their diet, their genetic makeup, and so forth. So you could have a lot more variables. And the other thing is that in the example of predicting weight from all these other factors, there's going to be some uncertainty. I can have two people who are the same height, the same age, and the same gender, but have quite different weights. Part of that might be variables that I hadn't fed into my equation, and part of it is natural variation or measurement error. It's important to remember in all of this that a model is a simplified version of reality. There's a trade-off between model complexity. The more terms you include and the more complicated you make the form of the equation, the better the model will match the reality, but the harder it will be to use the model to understand what's really going on. If I can explain 95% of what's going on with an outcome with one or two variables, that's probably much better than explaining 96% of what's going on with 1,000 variables with complicated interactions. So there's this important trade-off, and there's actually a famous quote from a statistician named George Fox who said, all models are wrong, some models are useful. You're never going to get a model that perfectly fits reality. That would just be reproducing reality. The important thing is to try to get a model that is simple enough that you can understand it, but good enough that it explains what's really going on in terms of the underlying mechanism. All right, what sort of statistical techniques should you be using? Well, that depends on the problems that you're answering. So a really important component of that flow chart that I was talking about earlier is to figure out what kinds of variables do you have. Do you have a binary variable or a continuous variable? So, for instance, are you trying to model whether somebody lives or dies, or are you modeling how long they're going to live after a diagnosis? Similarly, for the predictor variables, the things that you think might be disease risk factors or protective factors, they can come in many different flavors. And depending on the combination of variables you have and the problem you want to answer, that will determine on the model what the model type should be. The study design is also very important. Is the study observational? Is it a randomized clinical trial? Is it a cohort design? There are also, with any model, a number of assumptions that you make. And you have to decide whether the assumptions that go with a particular model form are correct or not, or at least whether they're close enough so that you can justify making the assumptions. And then the final piece, and this is by far the most important, is to determine what question you really want to answer. When I work with a student or a faculty member who's putting together a grant proposal or writing a paper or trying to design a thesis topic, this is the thing that we actually spend all the time talking about. It's not so much what the mathematical model would be. Once you know what the question is, that's actually usually pretty obvious. The hardest part is framing your scientific question in a way that's very clear and precise so it can be translated mathematically. So the most important lesson before you go and meet with a statistician, if you're doing that, is to try to identify very, very clearly what question you want to answer. So I'm going to spend the last part of the talk running through a couple of fun examples. The best way to learn statistics is actually to practice it. It gets more natural as you do a lot of it. And the important part is not doing all the calculations. I'm not going to do a single calculation today. The key thing is getting the right pictures, getting the right output, and then making the correct interpretations. And you'll probably do better with this if you pick as examples things from the world around you where your intuition can help you out. So hopefully the following examples will do that a little bit better than coin flipping. One of my absolute favorite examples is actually our criminal justice system, our legal system. It turns out that our entire legal system is basically a perfect analogy for hypothesis testing. So when you do a hypothesis test, you have a null hypothesis. That's the thing that you assume to start with, or barring any contrary evidence. And it's usually the thing you want to disprove. The alternative is that something interesting is happening or the thing you want to prove. In the legal system, the null and alternative hypotheses are innocence, that's what we assume by default, and guilt, which is what the prosecution is trying to prove. Instead of the data that you would collect to do a formal mathematical test, in a trial, the evidence that is presented is the data. And the question is whether that evidence is convincing enough to make you reject the null hypothesis of innocence in favor of the alternative hypothesis of guilt. You're only going to make that rejection and convict the person if the evidence is beyond the standard of a reasonable doubt. In hypothesis testing language, that's the significance level alpha. If you're convinced beyond that standard, then you reject the null hypothesis. That's just reasonable doubt that the null hypothesis is true. And of course, you end up convicting if the evidence does put guilt beyond a reasonable doubt, and that translates to the p-value from my hypothesis test was smaller than alpha. My data were extremely unlikely to have happened if the null hypothesis was true. In the legal setting, it's very unlikely that the prosecutor would have been able to present all this evidence against the defendant if the defendant were really innocent. Okay, so that's hypothesis testing in a nutshell, on display in courtrooms every day, hopefully being interpreted correctly. Switch over to NASA. NASA needs statisticians very badly. In fact, they've had a number of incidents where a statistician in the room would have been a really good idea. One example was the Mars Climate Orbiter. This went off course basically because two different groups were programming different parts of it, and one of them used metric units and one of them used British Standard units, and so it was lost and $1 billion went down the drain. That's not even a statistics question. There's no uncertainty there. That's just unit conversion. An example that requires a little bit more was the crash of the Space Shuttle Challenger. I started using this when I first taught, and at that point, most of the people I was teaching actually remembered the explosion the way I did. Now, most of my students don't, which is a little bit depressing. This happened on the 24th of the Space Shuttle launches, And basically what the concern was is that it was going to be very cold the morning that Challenger launched, well below freezing. And the engineers thought that the cold might crack the O-rings that were stabilizing the fuel tanks, and that if that happened, there could be a catastrophic explosion. So they had a meeting the night before the launch to actually look at the data. Unfortunately, there wasn't a statistician in the room, and they did the wrong analysis. The result was that there was an explosion, and not only that, because school teacher Krista McAuliffe was on board to broadcast from space to elementary school children, there was a massive live TV audience as it happened, which was extremely traumatic. So here's the picture that was actually being looked at to decide whether or not to launch the Challenger shuttle. And basically all this is a plot of launch temperature and the number of O-rings that had failed on previous flights at those temperatures. So what's plotted here is all the flights on which there actually was an O-ring failure, either 1 or 2. And if you look at that, there doesn't seem to be that much connection between the temperature and the number of failures. However, there's something missing from this picture, which is that they didn't include all the flights that actually went okay. That's a straight line indicating that nothing is going on, or if anything, the number of failures is maybe slightly higher at higher temperatures. Now, if we include all the data, including the flights where there were no problems, we see immediately that there's a big issue. It's true that there were some flights at high temperatures that had problems, but there were no flights with no problems at low temperatures. The Challenger launch was going to be below freezing, and you can see from this that if you extrapolate back, the likelihood was that there were going to be on the order of 3 or possibly even 4 O-ring failures out of 6, and some more fancy analyses were used to get an estimate of the probability of an explosion and conservatively put it at about 1 in 7. If they had really done that analysis the night before, which they could have done with this very simple plot that you get in Statistics 101, they would never have launched the shuttle. What model goes along with this? Well, the graph that we were looking at clearly suggests what the problem is, that the number of O-ring failures, or the chance of an O-ring failing, goes up as the temperature drops. How would we quantify this? Well, you can calculate the probability that there is any failure on the flight. That's what's called a logistic regression model, because the outcome is yes or no, fail or not. We could treat the outcome as continuous, okay, so just how many possible failures, or we could actually focus on the fact that this is a count. There could only be 0, 1, 2, 3, 4, 5, or 6 failures, and that involves using something called a Poisson model or possibly an ordinal logistic model. So again, how you think about the variable involved, fail or not, count the number of outcomes, determines the model that you would use. Another nice example comes from college admissions. So universities regularly get some grief for perceived biases in their admission processes. But there are a whole lot of factors that determine who does or doesn't get in, and it can be hard to tell whether there's a real problem. The following example is from a discrimination complaint against UC Berkeley based on gender in graduate school admissions, and it illustrates this very nicely. It looks on the surface as if Berkeley favored male students. 44% of men who applied were admitted, and only 35% of women who applied were admitted. However, if you break it down by department that the students applied to, it actually looks very, very different. So it turns out that the women were applying to the harder to get into departments. And once you accounted for that, the apparent gender bias went away. So this particular plot, which you can look at in more detail later, shows the percentage admitted, male and female, within each department, and it shows the number who applied to each department. The first picture, you can see that the women are not really doing any worse than the men in any of the departments, but there are very big differences in which departments they apply to. Okay, so again, the graphics tell the story. We don't really need a model or a p-value to tell us what's going on, but we have to make this into a model. Admission, again, is a yes or no decision, so a logistic model. And we're interested in whether the probability of admission is the same for men and women or different. So gender is our main predictor. However, because the department matters, we need to adjust for that in the model. So really the test we want to do here is not just are more men admitted to Berkeley than women, but is there a difference in male and female admissions after adjusting for the field of application? In other words, an incremental effect of gender on top of department. And the answer to that, according to the graphs, is not really. We could also look at interactions, whether the gender gap differs by field, which would require yet a different kind of model. I'm going to finish up with a couple of examples from elections. We probably don't have time to go through all of them because I want to allow for a few questions, but I'll highlight a few and you can look at the slides for the rest. It turns out that elections are a really good setting for looking at a bunch of statistical concepts. So here are a few examples. I'm sure that you all remember hearing about the election in 1948 between Republican Thomas Dewey and Democrat Harry Truman. This was the first election in which they'd really done pre-election polling, and the polls all showed that Dewey was well ahead. However, on election night, exit polls showed Truman winning in a landslide. And in fact, people disbelieved that so badly that they held up the results, but the exit polls were right. What went wrong with the earlier polls was that this was being done via random digit dialing. And it turned out that only wealthier people had phones at that stage, and wealthier people were also more likely to vote Republican. In other words, they got a biased sample. We no longer have the problem that most people don't have phones, so you might think that we would now get a representative sample that way. However, it turns out it swung the other way. People now may have multiple phones. They may use only their cell phone. We're all getting really sick of being called by people polling us or wanting to sell us something, so response rates are getting worse and worse. And then there are also issues about how likely people are to vote, which is different for different groups. So in fact, the issue of having to adjust polling models for lots of different factors is getting harder, not easier. If you want a fun, complicated, interesting job, you can go work for Gallup. Another thing that comes up in elections is the margin of error. So when we hear the results of the poll that are being conducted, we get something like Clinton leads Trump 53% to 47%, margin of error plus or minus 4%. What is that margin of error? Well, it's really just a confidence interval. What those polls always give you is the range that they're 95% sure includes the true proportion of people who support one candidate or the other. And the result of this is that the national polls tend to be more accurate than state or local polls because they include many more people, and there's probably been more work on selecting the representativeness of the sample. It turns out that in the last election, although there was all sorts of talk about the polls being wrong, in fact, the national polls, the final result, was within the margin of error. However, we don't base the final determination of who becomes president on the national result. We do it based on the Electoral College, which goes state by state. And several of the states that swung the election did not have all that much polling and had less accurate polling. So the election turned on that, even though the polls were not, in fact, horribly, horribly wrong. Let me see. Let me skip to gerrymandering because that's a hot topic right now. So as I'm sure you all know, gerrymandering involves manipulating the boundaries of election districts so that they favor or disfavor certain types of voter. There can be racial gerrymandering, there can be partisan gerrymandering. There are all sorts of ways that you do it, and you can usually spot it, again, with a graphic on a map by seeing that the districts are really funny shapes, meant to pick out or go around different groups of people. The result of gerrymandering in a statistical sense is what's called bias. So the overall results from the state don't match what you get district by district. And it's also, in a statistical sense, an uneven weighting of the votes. So we have this very important principle, one person, one vote, but when you gerrymander, people of certain types get put together and underweighted, and people of other types get spread out and overweighted. And this has now actually become a big statistical science. People who want to design election districts build complex statistical computer models. This can be used to draw districts that are fair. It can also be done to draw the districts that produce the best possible results for a certain group of people. And in fact, there's a major Supreme Court case right now, Gill versus Whitford, which is looking at partisan gerrymandering in Wisconsin. And with the map shown there, this was drawn by the Republican state legislature, and the Republicans ended up winning about 2/3 of the seats, 64 out of 99, even though the statewide vote was only about 52% in their favor. So a huge difference between the overall voting percentage and the resulting representation in their assembly. And the courts have never actually ruled definitively on whether partisan gerrymandering is constitutional, but one of the issues that has come up is how do you in fact quantify how much gerrymandering there is? How bad a gerrymander is too much? And so social scientists, including a professor at the University of Chicago and one at the Public Policy Institute of California, have been pushing a new statistic called the efficiency gap, which is supposed to help quantify gerrymandering. And it looks at basically how many votes for both parties were wasted by there being above the number needed to win a particular district, and then looking at that difference across the whole state. So mathematically, this is a very simple idea, but it may actually provide a handle that the Supreme Court could use to say, this is how we decide what is too much. Other places where statistics comes up in the census. The census is actually one of the few places where you're supposed to get a population survey. You ask everybody, but even so, that doesn't really work. There are people who get missed. And so it was suggested that statistical sampling techniques be used to adjust the census to try to count the people who you didn't actually get by going door to door. And there were major statistical experts as witnesses on both sides in various trials about this, debating the accuracy with which one could model the undercounts or overcounts. Shows up in sports. I'll just finish with this example. This comes from my being in LA, of course, where the Lakers are the favorite team. And they had two players for a while together, Shaquille O'Neal and Kobe Bryant. Kobe Bryant was a great shooter, a great free throw shooter. Shaquille O'Neal was a horrible free throw shooter, under 60% for his career. And I'm going to take some data from one particular game in 2000 where the Lakers were playing the Cleveland Cavaliers on their way to a string of 3 championships with Shaq and Kobe together. And at the beginning of the game, Shaquille O'Neal hit his first free throw, but Kobe missed his first free throw. Based on that data, we could estimate their free throw success. And the estimate we would get would be Shaq makes 100% of his free throws, Kobe misses 100% of his free throws. Do you think that Shaq is better than Kobe based on that? Well, of course you don't, because the sample size here is only 2. By the end of the game, Kobe Bryant had hit 13 out of 14 free throws, or about 93%, and Shaquille O'Neal had hit only 5 out of 13, or under 40%. Is this convincing? Well, it's more convincing, right? We at least have a lot more data, but is it enough? The way we answer that question is that we calculate a p-value. What is the likelihood that Kobe would have gotten 13 out of 14 and Shaq only 5 out of 13 if really they were equally good? And it turns out the chances of that are only 1 in about 370. So in fact, even this small sample from one game is pretty suggestive that Kobe's better at free throws than O'Neal. I'm going to stop there because I could go on with examples forever, but I want to leave a few minutes for questions. Basic conclusion, statistics isn't as different as people think it is from other disciplines. Once you learn the language and the logic, and how to apply it to real world situations. You should feel comfortable using it. And the best way to do that is to see a whole bunch more examples, and there's a wonderful site of Hans Rosling's called The Joy of Statistics, which has really excellent graphics, videos, and examples if you want some more. So I will stop there.
Thank you very much, Dr. Sugar. There are no questions. Oh, we just got a question. And it is, what are some recommendations for reviewing basics of formal logic or other resources for strengthening math statistics foundation?
Okay, so it's probably not going to help if I just try to list out a bunch of books online, but I can certainly send a list of some books that you could use. There are a lot of sort of logic for dummies kinds of books which are pretty good. There are also books of puzzle problems. So my kids have some books about one of the best kinds of problems is the liars and the truth tellers. So you have people on an island some of whom always lie and some of whom always tell the truth, but they look identical. You can't tell them apart, and so you have to try to decide based on a series of statements that they make who's the liar and who's the truth teller. And all the basic principles of logic can be illustrated with those games, and they're lots of fun. So I can certainly send some links to some books like that, both with fun logic puzzles and then some of the formal rules, and also some good search terms. There's lots of the basic logic rules available on the web if you're looking at the right link. So I'll certainly pass those along. In terms of recommendations for books, there's actually a really nice book that's called something like I'm trying to remember exactly what it is, the Cartoon Guide to Statistics, which is a really nice basic one that goes over a lot of the principles in a fun way. So that's a good place to start. If people have questions about very specific statistical techniques, I can certainly recommend particular books for that. There are accessible books in almost every area if you know what it is you want. In terms of math, if you still actually have hiding in your closet somewhere your high school algebra and trigonometry book, it probably has a lot of the basic math that you would need to remember. Things like polynomials, logarithms, exponentials, summation notation, what basic functions like parabolas and logarithms look like. So if I had to just pick one math book, I really might go back to my high school math book for that.
Oh, thank you very much. By the way, on our website, we archive each of these presentations, and we also include, when they're provided, links to more information. So we'll post those, whatever Dr. Sugar shares with us, we'll post those next to the archived presentation. We have one more question. Can you talk about statistics and the trend towards big data, for example, the Precision Medicine Initiative cohort?
Sure. So big data has obviously become a major buzzword. Data science has become a major buzzword. Precision medicine has become a buzzword. I find the term big data by itself not ideal, largely because it's not terribly well defined. So there are lots of ways that data can be big. You can have lots and lots of people, but not terribly many measurements on each one of them. You can have not very many people, but a very, very large number of measurements. So for instance, if you do a microarray experiment, you might have a relatively small number of subjects, but a very, very large number of gene expressions. And that's a different sort of statistical problem. You might have a large scale computational problem because you just have so many people and so many measurements that it's hard to get them all together in one place. When that's the case, then statistical inference changes a little bit, because with enough data, almost any effect is significant, even if the effect is very, very small. And so you really have to define much more precisely what kinds of effects or patterns you're looking for, rather than simply asking the question, is this significant beyond chance, which is the way that we've been brought up to think about statistics. So I think one of the things that's really important to be aware of is how having vast quantities of data changes your question. Another thing that comes up when you have really massive data like that is that there are usually a lot of holes in it. So any study can have some missing data. You have people who drop out before the end of a trial, or maybe they didn't give you certain demographic information or things like that. But when you have big data, where you have maybe the phone company is recording data on thousands and thousands of measurements, or say Netflix is trying to record what movies people like, there you have a really massive problem. They have lots and lots and lots of users. And you also have lots of variables, all the movies or telephone services that they might be using or evaluating. But you certainly don't have a rating from, say, every Netflix customer on every movie. And so the data are what are called sparse. There are a lot of holes, but still somewhere in all of that, you ought to be able to pick out patterns or relationships. The same thing is going to be true of data for precision medicine on any given patient. You're going to have lots and lots of measurements, but not all the possible measurements of things that might go into personalizing treatment for them. So I think that we're still a long way away from being able to take all the information that's available about a certain person and saying with any kind of high confidence what the perfect treatment for that person is. When you take it down to the level of one individual with very, very, very specific characteristics, your sample size, of course, has gotten small. The way that we generally make inference about what is good treatments is that we pool together a lot of people who look similar and see how various treatments work for them. But the more different factors you add, the fewer people you have who look like that, the harder it is to make a prediction without making a lot of assumptions about what the basic nature of the relationship is. So this is a big ongoing area. I don't think anybody has a magic bullet yet, but on the other hand, more and more data is becoming available on a large scale through electronic medical records, which is going to give statisticians the opportunity to build models that might work, at least if you believe in the extrapolation to the individual patient. So this is an area where I think there's a lot going on. It's one of the most exciting things in statistics. And almost every statistician is working on this some way or another.
Well, thank you very much, Dr. Sugar. Those are all our questions, and we're going to conclude our webinar today. I just want to remind everyone that this will be posted on our exitotraining.org website. When the links are provided from Dr. Sugar, we'll also have that additional reference information. You'll also all be given a very brief survey. Please fill it out. It's very helpful for us in planning future webinars. And until next time, thanks very much for attending.